Hi. Hi. So today we're going to think about non-determinism in Turing machines, and in particular non-deterministic polynomial time. So let's start in thinking about non-determinism. Oh, if I can find my mouse, where the heck is my mouse? There it is. Okay. So you remember from finite state machines that a machine is non-deterministic if from the present configuration and the input it can pass to a next configuration that where the number of states is 0, 1, or more than 1. That contrasts obviously with the deterministic machine where you know where to go next. So with a non-deterministic machine, you can find yourself next being in 2 states or 3 states or 4 states. It could happen to you. You'll remember that that we have 2 mental models of how these devices operate. In the first, the machine is unboundedly parallel. So when we're called on to go into multiple states, the machine will just split, and there'll be multiple places where it goes. So for example here, suppose that you have a machine that starts off and then is called on to split into three separate states, and then up here it might split into 2, and down here it might might go to a terminating branch, and then down here it might have a branch that never terminates, and both of these branches maybe terminate. Maybe down here there's another branch that after some fiddling around will accept the input sigma. So we're looking at a sort of a computation history here. Oops, trying to edit my picture and it's made a mess of the whole thing. We're looking at a computation history here where it's a tree. It's not a straight line, it's a tree. In the second mental model, in the first mental model, darn it, I keep losing my mouse. In the first mental model here, the machine is unboundedly parallel and we follow all the tracks. In the second mental model, the machine doesn't follow all the tracks. Instead, it guesses. It guesses what to do next. Or maybe if you don't like the word guesses, it makes you nervous in this context. Maybe you'll say, well, the machine gets a hint from some being that doesn't have to do the computation, so we call him a daemon, like Maxwell's daemon. And then what it has to do then is though deterministically check that branch of the computation tree. So here, for example, there's an accepting branch, and the machine might get the hint to take the daemon might say, I got to draw the daemon. This is embarrassing. The daemon must need horns, right? Sorry about that. So the daemon might say, take the third branch, and then take the second branch, and then there is no branch, and you'll find yourself at an accepting state. You will have accepted the string. So in that second mental model, the machine is somehow gets information, and all it's got to do is deterministically verify. Okay, so these 2 mental models, I hope, familiar from the case of finite state machines, where we talked about them a lot, precisely for this moment, so that we're ready to have the conversation that we're having now. Described in the language of the first model, we say that the input string is accepted if one of the branches on the tree is an accepting branch, if there exists an accepting branch on the tree. And described using the language of the second model, that means that the input is accepted if there's a sequence of guesses that the machine could make, or a sequence of hints that you get from the daemon that leads to an accepting state, and the machine has to verify them. That leads to an accepting state. These 2 models are equivalent. These 2 mental models are equivalent in that for a given non-deterministic machine, they yield the same collection of accepted strings. If your input sigma is accepted in the first mental model, then your input sigma is accepted in the second mental model. And we're using these mental models as a way to help us to understand what's the right definition to make. What is it that we want these machines to do? How do we express that? I like to think of non-determinism in terms of an actual concrete problem, and to me, the concrete problem that works the best is the traveling salesman problem. So you have a map of the United States. You want to start at the capital city of one of the states, and you want to go around the United States. You want to find the circuit around the United States that takes you from capital city to capital city to capital city and back to the original capital city in the minimum amount of distance. So the two mental models are, first of all, you try every possibility. You start from the capital city, Montpelier, Vermont, and then you branch a child that goes to the capital city of Albany, New York, and you branch another child, etc. So from the capital city of Montpelier, Vermont, you would go to the 47 other lower 48 state capital cities, 47 children. And each of those children would have 46 children. And it's that. So you're branching, tremendously branching tree. But if there's an answer that is less than, say, 16,000 kilometers, somebody's going to find it. So the machine is in many states at once in this picture because you've got all these children working. And so the machine is checking all possibilities by brute force, by actually checking them all. So that's the first mental model, the branch everywhere model. The second mental model is you don't branch everywhere. Instead, the machine guesses where to go. The machine guesses Albany first, and then guesses its way around the United States. Now, we say that circuit is accepted in the first mental model if there's at least one of the branching processes that finds a circuit that's less than 16,000 kilometers. And that makes sense. A person nods to that. You say, well, I get it. I get why you would say, except if somebody finds a less than 16, that makes sense. In the second mental model, the one that makes people a little bit confused, the guesses mental model, or the demon mental model, in the second mental model, we say, if there were a way to guess, not how do I do it, if there were a way to guess, then we would accept. Okay? And those two models are equivalent because if there is some branching child, then there is a way to guess. And if there is a way to guess, and you tried every possible way, some of the children would find it. Okay, so those two models give the same collection of accepted strings. Okay. Now, that final sentence raises 2 points. Right, before we go to the definition. That final sentence raises 2 points. First, once some branch accepts the input, we might as well stop the computation. If we find a 16,000 kilometer circuit around the United States in the traveling salesman problem, you might as well stop. There's no need to go any further. You found it. The answer is yes. Second, the seemingly could be, if you're doing this computation, if you're guessing, it seemingly could be you could find yourself trying to, in a problem where you're trying to guess, and you end up in some kind of loop. Could you go for a loop where you're going back and forth between Montpelier, Vermont, and Albany, New York, and you never guess some kind of crazy stuff like that? If you're guessing, I would think so. But we want to use these machines as language deciders. We want to define non-deterministic Turing machine in such a way that we use them as a language decider, and you can't time it if it's going to go on forever. So we will, in the definition that follows, we will require that the machine, it will only say the machine is a language decider if all branches, even the ones that fail to accept, all branches hold. Okay, and that's just a question of we want to be able to time it. Okay, so here we go. Here's the definition finally, after a lot of setup and a lot of thinking about demons and all kinds of stuff. Finally, we get to the definition. Let P be a non-deterministic Turing machine such that every branch of the computation tree, that is to say, I'm defining a branch of the computation tree, every sequence of valid transitions from the starting configuration, we did those setups with yields. Every sequence of valid transitions from the starting configuration is finite. So I can time it. I can say which one is longest. then P accepts the input string if at least one branch ends in an accepting state. At least one branch. That's, you think of the traveling salesman problem. That's one of the problems we want to think about. If at least one branch finds a short enough circuit, we want to say, yes, we're done. Otherwise, if there just simply is no branch, then we reject the input. That's what makes this machine a decider. It either accepts or rejects. It doesn't leave itself saying, I'm not sure. I'm still waiting for the computation to finish. The machine decides a language L if every input string, if for every input string, when the string's a member of L, then P accepts, and when the string is not a member of L, then P rejects. Okay, so the machine rejects in a finite time because every branch finishes in a finite time, and you can say the computation has finished. The answer is 0. So that is to say, this machine computes. Darn it! Come on! Oh, darn it! Oh boy, I really messed it up. Oh, I see. Okay, this machine computes. P computes the behavior that is the characteristic function of the language L. P computes the characteristic function of the language L. So we end up with a function, namely 5 sub P, that is the characteristic function of the language L. You get yeses, but you also get nos. That's what we mean by decider. So no recognizes, decides. Okay. What did I do? I don't know what I did. So, first point we want to say is that for Turing machines, deterministic and non-deterministic machines decide the same languages. In one direction is easy. Deterministic Turing machine is a special case of a non-deterministic Turing machine. So if the deterministic machine decides a language, then the non-deterministic machine does also, because trivially. So there must be a hard half. So we're going to do the hard half. So a lot of times with these lemmas, there's an easy half and a hard half, and we're thinking about the hard half. All right. So let's see. I'm going to draw here a machine's computation tree, and I'm not going to remember what I drew last time. So I'm going to draw a new one. I remember there were 3 initials, but I'm not going to remember the rest. So maybe there's 2 here, and maybe there's 2 here, and maybe 1 more, and then maybe there's another one here that runs a little longer but doesn't go on forever because we've eliminated that in the definition, and then maybe here and here. Okay, and then accepts. So again, one direction is easy. The deterministic machine is a special case of the non-deterministic one. So automatically, if the deterministic machine decides, then there is a non-deterministic machine, namely the deterministic machine, that decides also. So that's good. The second case, though, is you start with a non-deterministic machine, and here I've drawn it, and I want to. Oops, what happened to my mouse? There it is. And I want to write a deterministic machine that computes the acceptance. Okay, so I think you see what to do. So you have the non-deterministic machine, and I'm describing its computation tree. I need to produce a deterministic machine, and I call the non-deterministic machine P, so I call the deterministic machine Q because I'm not a very imaginative person. It's going to go through this tree and do a breadth first search. It checks that node, then it checks node, 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 and it says, has that branch terminated at an accepting state? No, in all those cases. This branch has terminated, but not at an accepting state. This branch has terminated, not at an accepting state. Not terminated, terminated, but not at an accepting state. So you see what's happening here. The machine is checking off every one of these nodes, and it's going to keep saying waiting, waiting, waiting until it works through the whole tree, or it finds, it found an accepting state that's at the end of a branch, and it says ding, 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 ding. Q says ding, 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 that P accepted the input string. Okay? Okay, so what we have then is the breadth first search eventually exhausted all the branches, so Q accepted sigma here. If, on the other hand, the breadth first search exhausted all the branches and didn't find any accepting, then Q would reject. Okay, so we have the definition, talked a lot about where the definition came from, and now we have the definition. Why? What's it good for? Okay, fair enough. What's it good for? Whoops. Fair enough. What's it good for? So, the answer is that it at least appears that non-deterministic machines, if we had them, or if we just simply imagine having them, non-deterministic machines might be faster than deterministic machines. Why does it appear that? So of course here's an answer of why it appears that. So consider the satisfiability problem. So here's a propositional logic formula. It's got one clause, two clause, three clause, four clause, five clauses, and I'm asking, is it satisfiable? Is there some assignment of truth values to P, Q, and R? They have three letters, P, Q, and R, that ends up with a T. And the natural thing to do, if I gave you this, if I gave you this expression and I said something like, I'll give you $10 if you tell me it's satisfiable, well, I think what you'd do is you'd write down its truth table. Isn't that what you'd do? You write down its truth table, and there's the P or Q computation. Here's the P or not Q computation, etc. And you do the whole computation until you got to the end, and you would find that there is indeed, in this case it happens to be exactly one line, there is indeed a line, the TTF line, there is indeed a line that ends in a T. So you'd say, yes, it's satisfiable. For a deterministic machine, at least naively, for a deterministic machine, it appears that in order to find that line, you need to check the first line, and then the second line, and the third line, and the fourth line. And that's all fine. I only had 8 lines to check. It didn't take me all that long. But it's clear, isn't it, that the number of lines is 2 raised to the number of variables. That is to say, it at least appears that a deterministic machine, a serial machine, a 1, 2, 3 machine, seems to have to take exponential time to do this job. But a non-deterministic machine that can either guess the right line, or that can listen to a daemon, try the TTF line and then deterministically verify, because you can't believe a daemon, you have to check it. It appears that machine can do it very quickly. So it appears that there is a speed difference between a serial machine, a deterministic machine, and a non-deterministic machine. So we are interested in these machines because they seem, at least appear at first glance, to be able to do the jobs faster than a deterministic machine. Okay, so speed is the short answer. Why are we interested in non-deterministic machines? Speed. So the number of table rows goes exponentially. It's 2 raised to the number of input variables. Going through the rows serially would be very slow, but this problem, you think about it, each line of the truth table is easy. The issue is simply that there's lots of lines. So this situation is perfectly suited to unbounded parallelism. You think to yourself, if only I was able to spawn a child for each line, why, I'd be done in no time at all. So that's exactly what we're saying. We're saying that if only we had an NP machine, if only we had a non-deterministic machine, we'd be in business. Okay, so the non-deterministic machine does this job in polytime, while a serial machine appears to require exponential time. That anyone can figure out today, serial machine requires exponential time. Okay. So I'm ready to talk about the complexity class. Finally got to the complexity class, the second complexity class, the second most important complexity class, the complexity class NP, which is the set of languages for which there is a non-deterministic Turing machine, decider P, that runs in polytime. Meaning specifically that there's a polynomial P, so that on all input sigma, all branches of P's computation halt in time P of the length of sigma. Okay, so NP, P was the collection of languages for which there is a deterministic Turing machine decider. NP is a collection of language for which there's a non-deterministic Turing machine decider. So first thing to note is that P is a subset of NP, and that's simply because every deterministic machine is a non-deterministic machine. And so if you can do the job with a deterministic machine, you can automatically do it with a non-deterministic machine. So automatically, the collection P is a subset of the collection NP. So that's a free one. Now, we'll have much more to say about this later, but it would be unfair to go on without making the point here. I drew the picture earlier that consists of all problems. So this is all problems, all languages, subset of the Kleene star of the bit strings. There we go. The Kleene star of the bit strings. Come on. All problems. And I have two possibilities. Obviously, P's got to be a subset of NP. The question is NP greater than P, strictly superset, proper superset, or is NP in fact equal to P? All right, and the answer is, at this point in history, we do not know which of these two answers is right. We'll talk more about it as we move through. But the lemma makes clear that one direction is right. P is a subset. Is it a proper subset or is P all of NP? We don't know. But interesting question, and it's interesting precisely because we want to answer this. We want to talk about the speed issue. Okay. Last thing for this video is mathematical presentations often introduce an idea with a definition that's natural or that's conceptually clear, or at least all fits together in a sensible way that you can motivate carefully, like the motivation we gave before the definition of non-deterministic Turing machine. And then mathematical presentations often follow that with a result giving a characterization that's more convenient for actually doing the problems. This is a perfect example of exactly that thing. So the next lemma is a perfect example. To show that a problem is in NP, it's almost always the thing we use. We almost never use the definition of non-deterministic Turing machine. Instead, we almost always use this verifier definition. Okay, so here we go. It's a little tough. So we're going to work through it at some length. A verifier for a language L is a deterministic Turing machine, so that part's not so tough. A verifier for a language L is a deterministic Turing machine V that halts on all input strings. Deterministic, so you don't have to worry about different branches halting or not. And such that sigma is in L if and only if there is a witness or a certificate string, omega, that's an omega, terrible handwriting, omega. There's a witness or certificate string, omega, so that V accepts the pair sigma comma omega. So that is to say, V is a two-input machine. It accepts sigma and omega. Sigma is the candidate for being an element in L, and the witness is the demon's hint. The witness, the certificate, is the suggestion that you should use to do this problem in polynomial time. Okay, and then the lemma is that a language is in NP if and only if it has a polytime verifier. L is in NP if and only if there's a polynomial P and a deterministic Turing machine V that halts on all inputs in time that is polynomial in the length of sigma, and such that sigma is in L exactly when V accepts the pair sigma comma omega. And that lemma takes a little working through. It's been my experience that this lemma gives folks a lot of trouble, so we're going to give a number of examples and also have some careful discussion about it. A language is in L if and only if it has a polynomial time verifier. And the verifier, you remember, gets two inputs. The first is the string that you're trying to decide is it in the language or not. The second is some kind of hint, witness, certificate. So the daemon says to you, psst, try the TTL line. And you can quickly try the TTL line. So that is to say, you can, in polynomial time, on a deterministic machine, verify that that indeed sigma is in the language. So the proof of this lemma is, again, a little tricky. Tricky in the sense that it gives people trouble. So historically, this lemma gives people trouble. The definition of lemma gives people trouble, so I think that's a good definition, tricky. So we're going to do some examples and some discussion first. The definition says there exists a witness. I can't overemphasize this part. There exists a witness. It does not say where the witness comes from. So this formalizes the mental model. We spent all this time talking about the mental model of a demon providing an answer. It is for this exact moment, so that when I pull omega out of nowhere, I can say that it in our mental model of what's happening, the omega came from this demon. So the right example to think of for the definition in the lemma is the satisfiability problem. Imagine that the demon, you want to check whether you want to check whether a given expression is satisfiable or not. You want to check whether sigma is in L. So the demon whispers in your ear, psst, try the TTF line. And you can deterministically verify that hint very quickly. Checking any one line of the truth table is fast. The problem with the truth table was that there are many lines. Okay, so one example, and then we're going to end this particular video. In the next video, we'll come back to a discussion and do some more examples, just trying to make it all manageable. Okay, so our touchstone problem is satisfiability. So we're going to use the lemma to verify that satisfiability is NP. So we have to produce a deterministic Turing machine verifier. Obviously, there's going to be a verifier that I'm going to give you, and I'm going to say it does the job. It takes two inputs. Sigma is the Boolean expression you want to know, is it satisfiable? Omega is the demon's hint. Sigma is the Boolean expression. Omega is the demon's hint. So here's a flowchart. You see the two inputs. It reads in sigma and omega, and again, sigma is the Boolean expression. Sigma is the Boolean expression. And omega is the hint. Boy, my handwriting. Omega is the hint. So what would your verifier do? It would do exactly what I just said. Your verifier will compute the TTF line in sigma's truth table. Does it give T? Why, yes. Does it not give T? Reject. So if you got a hint omega, you could, in polynomial time, verify it and accept the pair sigma comma omega. So if there exists an omega, if there is a line in the truth table, if there exists an omega, then this will, in polynomial time, accept sigma comma omega. If there doesn't exist an omega, then it doesn't matter. It's not going to do it in polynomial time. It's not going to do it at any time. It'll never accept. So if there exists an omega, that is to say, if sigma is indeed satisfiable, then it will, in polytime, accept. So if a candidate expression sigma is satisfiable, then there's a suitable witness. There's a suitable thing that the demon could whisper in your ear, and you could check it in polytime. If, on the other hand, if the candidate sigma is not satisfiable, then it doesn't matter what the demon whispers in your ear, that you can't come up with, you can't check the omega in polytime or anytime because it doesn't work. What's an example of a not satisfiable expression? Here's a silly one, but nonetheless a perfectly good example. P and not P is not satisfiable. If the demon says to you, psst, check the TTF line, doesn't matter because it's not going to accept it. It won't give T. The answer will not be yes. Okay, so to close, we have defined non-deterministic Turing machines. And then we've gone on and given a lemma that enables you to compute whether a job is solvable by a non-deterministic Turing machine, the verifier definition and lemma. That verifier definition and lemma often gives people trouble, so it's time to stop and say, let's do a bunch of examples. Those examples are going to be on the next video. It's just a question of trying to make it all fit in one space. Okay, very good. So see you for that.